Hey everyone, welcome to today's talk. We're going to discuss how to debug hard faults on Cortex-M MCUs, and we're going to look at best practices. My name's Chris Coleman, and I'm the co-founder and CTO at Memfault, where we build developer tools for embedded engineers like yourselves. Prior to working at Memfault, I was an embedded engineer myself at Sun Microsystems, Pebble, and Fitbit, where I worked across the stack from low-level microcontrollers to boot code running on DDR4. One of the common threads between all of those was I've always enjoyed digging into and looking at some of the bugs or hard to reproduce issues happening on the system. Hence the chat today about hard faults. You can find my thoughts and some tips and tricks I've learned over the years on Memfault's interrupt blog. I encourage you to check it out if you haven't. I'd love to hear your thoughts. So Cortex-M hard faults. Why do we care? Well, in the last quarter of 2020 alone, over 4.4 billion Cortex-Ms were shipped. So if you haven't seen a Cortex-M, you will. And with that many out there, there's plenty of issues that will happen and take place. And there's two main places where hard faults get in our way. During initial development, when we're trying to get a feature out the door, you might hit an issue at your desk. And if you can't debug it efficiently, it will slow you down. But even more so, faults make their way into the field and can lead to a variety of different issues, whether it be bricking your devices or resulting in RMAs. Or in a worst case, ultimately hard faults are executing unintended code paths, and so they can be re-exploited and lead to security problems in your platform. And so something at all the places I have always wanted to do was something I've done at all the places I've worked was try to institute some policies where we track how often hard faults are taking place. If you see an uptick in faults on your platform on a system, it's a sign that something is going wrong. But what I often find is it isn't something that is tracked or looked at or a piece people think about today. So I wanted to do a quick, we'll launch a quick poll and see how many of you here today know how many faults are being experienced on your fleet. Give it a couple more seconds. I see some results rolling in. Great. Let's share the results here. So it seems like we're not doing that great as a crowd here today. I hope if you take nothing else away from this talk that you get something in place to understand these stability issues that could be impacting your platform. All right. So what I would like to cover and go through today is how hard faults work overall on Cortex-M platforms, what techniques we can take to examine them and the architecture. Go over the process where when you're at your desk and you hit a fault, what are the things you can do to examine and figure out what happens? How we can automate and accelerate that process so we can move efficiently and debug the faults that are taking place. We'll explore how the tools I work on at Memfault can be used to up the level even more and look at issues faster. And then we'll talk about how you start to build those numbers about what's happening at scale on your fleet. All right, so you've probably seen something like this before. We have a very sad function here on the left, buggy function. And what it's doing is we're writing a value 0 to an address that doesn't exist. When we do this, the processor is going to get upset. A hard fault handler is going to be invoked. Typically, some fault handling code runs in that hard fault handler, and the system will then reset. But there's a couple different pieces that are happening in between. And at this point, if we didn't know we were in that buggy function, we need to figure out what led to that hard fault handler being invoked in the first place. And so where I always start if we're debugging things that are happening locally at our desk is connect the debugger. I've seen a lot of setups in the past where there's only a serial connection or a USB connection. When a hard fault takes place, those parts of your system might break down or may not be working. And so you really want to have some debugger set up on your system that you can attach to step through and examine the state. When it comes to debuggers themselves, there's also sort of a wide spectrum of choices out there that are available for you to use. What I highly recommend for your MCU or setup is making sure, first and foremost, that the connection is reliable, not a setup where you have to hold a probe to the board or kind of glue some things together just to get the traces for JTAG to work, but choose a setup that both maps to your dev board well and also works well, that you can step through instructions and examine memory and look at pieces. The setup I typically use has been Seger's JLink plus JLink GDB server, which worked very well across a variety of different MCUs, and the GDB client itself to examine the system. When we're investigating faults, we're going to want to be able to read and write and examine registers in memory. And so you also want to make sure the debugger you're using allows you that degree of control. Most do, but some don't, so check that. And then the third piece is if we're trying to debug efficiently locally, we don't want to do the same thing over and over again. Unwinding registers and walking through things manually is error prone and can send you down rabbit holes. So once you understand the basics, you're going to want some degree of scripting to help you out. Once we have the debugger, the next piece that we need to look at is sort of how does the Cortex-M architecture work and what is in place. And the cool thing about what we're going to talk about today is the general principles for fault handling on Cortex-Ms apply to the entire family. And so regardless of what vendor or what MCU you're using, the fundamentals that we're going to explore today are going to apply for all of them. The ARM architecture classifies faults themselves into three main types: usage faults, bus faults, and mem-managed faults. Usage faults can be user configured. So there's things like divide by zero or unaligned accesses. It can also trip if you execute invalid instructions. Bus faults are the result of memory access errors. So these are like the one we first looked at, where we're storing something outside the bounds of memory. Mem-managed faults are typically generated by the memory protection unit. So if you're making use of a Cortex-M with an MPU, a fault will be generated if you read, write, or try to execute from a region where that has been walled off. The other reason a mem-managed fault can happen, though, is if you try to execute from a specific address range on the ARM microcontroller, it will always generate a mem-managed fault. One of the trickiest things about the middle fault, the bus fault, is that they can be imprecise. What this means is the fault may take place after the instruction executing, after the instruction that caused the fault triggered. And this is due to caching. On some Cortex-Ms, when you store, it will be written to a cache, and then several instructions later, the store will actually execute to the backing RAM, and that's when the fault would trip. And so that's something that you'll have to watch out for. On the right, we have a few basic examples of faults here. My favorite is the defined undefined instruction that a lot of compiler intrinsics have, built-in trap. And what this is it's an instruction that can intentionally be used to trap into a fault handler. For architectures that don't have breakpoints, that's often how they'll trip. And then the bus fault example is very similar to the one we were starting off when we looked at. And the mem-managed example is that a pointer casts that address range I was talking about that will trip and trigger faults. So once the system faults, the first thing I like to look at is the summary of what was happening on the system. And that's stored in a configurable fault status register. There's a bunch of bits here, a bunch of different pieces, but there's a few ones that I always like to check. The first are bits that will tell me whether or not the processor was able to capture the address which triggered the fault. So that's the bus fault address register valid and the mem-managed fault address register valid. What's useful here is if those are set, it means you can read from another register and find out the exact memory access that caused the failure. Then there's a bunch of bits that refer to stacking errors. And if any of these are set, it tells us that the processor failed entering or exiting an exception. And when you see those, it means a stack overflow or some sort of corruption was likely on the platform. And then the other two I really like to check are the imprecise and precise error bits, which tell us whether the instruction at the time the fault took place was the one that actually tripped and caused the issue, or if we're going to need to look in surrounding code to figure out what caused the problem. On the right here, for our buggy function, when we dump this register, what we see is hex 400 is set. So that tells us that that will tell us that it's an imprecise fault. And when we look at it, we'll have to examine deeper. So maybe you've seen something like this before. You hit a hard fault handler, and in your debugger, you type backtrace, and you see something that is completely nonsensical or not very useful. There's two reasons this usually happens. One, if your hard fault handler is doing some cleanup or modifying registers of its own, it's possible you passed the point in time where the debugger was able to recover useful information. And the second part is when you enter an exception, it is a lot of debuggers don't have the best infrastructure in place to unwind through exceptions or issues. And so what we need to understand when we're recovering the call stack is what state is updated and what we need to look at to get things in place. And that relies relying a little bit on that. And so let's break it down. So to solve the first problem of blowing past the beginning of the hard fault handler and updating other things, what I like to do is enable the hard fault, a feature of the Cortex-M microcontroller, the hard fault vector catch. And what this will do is when a debugger is attached, it will halt the processor immediately at exception entry. And so you'll be able to halt and look at the state before anything else has been clobbered. And to do that, there is just one bit that needs to be set. For the second part, we need to understand a little bit about the Cortex-M architecture and its modes of operation. So there's two main modes that the Cortex-M microcontroller operates in: thread mode and handler mode. Thread mode is the mode that's typically running when your system is live and active. And handler mode is a special mode that happens when a fault or an interrupt take place, which are confusingly referred to as exceptions in the ARM Cortex-M reference manual. When the handler mode is done executing, it can either return from the exception back to thread mode, or you can reset the system in the case of a fault. For the different modes, there's different stack pointers that can be active. They're referred to as the main stack pointer and the process stack pointer. The reason there's usually two stack pointers that are used is you get better isolation between your interrupt handlers and your main code handlers. So if you, for example, are running off the end of your process stack pointer and that triggers an exception, your exception handler will still be able to run because that's a different stack pointer. And what you can do in GDB or any debugger is dump these registers. And what you'll see is that that PSP or the MSP will always point to, one of them will always point to the SP, which is the active stack pointer. The other piece of information that we're going to need to understand a little bit is how the Cortex-M core registers work. And that's what's really neat about this in general is the ARM architecture. They define application binary interface that a compiler must follow when you're entering and exiting functions. And the super cool thing is exceptions, or the exception handling mechanisms for the microcontroller, have to abide by the same conventions. And so the way the compiler emits calls between functions is, we're going to find out, is the same thing that happens when we're entering exceptions as well. And so there's three classes of registers. There's what are referred to as caller saved registers. These are registers that a routine must preserve if it expects them to survive across a call to a subroutine. And then there's callee saved registers. These are registers that must be saved by the subroutine and return to their original value when things return. And then there's several special registers. These are used to sort of track the execution state of the system. So we have the stack pointer, which points to the lowest point in the stack that's active, the link register, or the LR, which holds the address to return to. So if you're in subroutine, it will hold the address routine to return to, and the program counter, which points to the next instruction to execute. And so with those two pieces in place, what we can do is see how those map over to our hard fault handling logic in general. So we're back to that initial example, buggy function. We do this bad right. And the first thing that happens is the hardware detects the fault, it intercepts it, and it saves those caller and special registers to the stack that was active. And so on the right, you'll see a representation of that, where we've pushed the R0 through R3 and R12, the caller saved registers. The special registers. So that's going to be the link register that was going to be returned to, and the PC, or sort of the next instruction to execute. There's a special register, the program status register, which is used for holding a little bit of additional state we'll get into. And then if you're using a microcontroller with a FPU, there may also be some registers that need to be stored there if they were in use. And then finally, that application binary interface we talked about, it states that when you enter external functions, your stack must be 8-byte aligned. And so if the stack at this point is 4-byte aligned, there's a padding byte that will be pushed automatically to the stack as well. And so once the hardware has saved our stack, it will jump to the next phase where it updates a few of these register values automatically for us. It switches the stack pointer. If the PSP was in use, it'll change it to the MSP. It updates the link register to a special value known as exception return. And we'll get into this, but what exception return does is it basically encodes to the hardware how to unwind that stack that was just pushed. And then finally, it will update the program counter to the address of the handler to invoke. So in our case, when a fault takes place, the hardware will look up the address of the HardFault handler in a vector table, point to that, and then finally we're in our HardFault handler. So when we enter an exception, the first thing, and that vector catch strips, the first thing I like to look at is some of these register states. They give us some interesting information. The XPSR actually encodes the exception that was active or in use. So if we look at that, what we'll expect to see is 3, or for a hard fault. And then there's another bit that's encoded as to whether or not that padding byte was active. And then in the exception return register, we get a few useful pieces of state as well. One is bit 2 will tell us whether or not we're returning to the process stack or the main stack. This is crucial for us to get those registers that were saved there. The bit 3 will tell us whether we're returning to thread mode or handler mode. And where this is interesting is if it's not set and you're returning to handler mode, it tells us that the exception was triggered from an interrupt or from another exception versus usermillion code. Bit 4 will tell us whether or not those FPU registers were pushed, and we'll need to use that to recover our stack. The part that's interesting about the exception return value is the upper bits are always going to be set to 0xF. And so if you're looking at registers, or if you halt your system and you see a bunch of Fs in the link register, it's not corrupted. It's probably in an exception, and that's where it's going to return to. All right, so with the foundational pieces in place, let's go about recovering the information. And so we have our buggy function. We've tripped into it, and this is all we get. And so the first thing we can look at is recovering that call stack. And so what we can do there is look at that exception return value to find out the program stack pointer that was active. We can then look at the XPSR to figure out if that padding bit is used and compute the sizes we need for the exception frame. And then finally, we can unwind the information on the platform so that we can set those registers to the state they were before the exception executed. And by doing this, GDB is going to be able to give us an accurate function unwind. And so putting it all together, we start with that backtrace that didn't make any sense. We recover our exception frame, recover the length, restore those values, and we see we get something much more sensical. A buggy function was called from a CLI command that was a test buggy function. All right, so that's great. Like you made it through it. You understand a little bit more, hopefully, about how the exception handling works itself. You probably don't want to do that every time. And so what I highly recommend is scripting the analysis. We're using GDB today, and so I'm going to talk about how we can go about doing that with GDB, but most debuggers have some form of scripting that can be used as well. GDB itself has a couple options out there. The examples I'm going to give here are using GDB's internal scripting language, but the ones I really like taking advantage of is their Python API, which builds on top of their foundation, but then you can use Python packages as well to advance or make your analysis more sophisticated. And so the first piece we're going to do in scripting is automatically enable that vector catch feature. This way, anytime a hard fault takes place on your system, you'll get halted and see the state. If you're using CMSys, the default hard fault handlers are actually while one loops. So maybe you've typed some code before and seen your system hang and not know what's happening. If you enable vector catch, even in that situation, it will halt automatically. The next piece we're going to script is some of that fault register analysis, the ability to look at the CFSR, and then if that bit set about the bus fault address being valid, we'll read that as well to figure out what address triggered the failure. And the third piece we'll script is that restoring the state of the stack before the exception, so that we can unwind the stack to its pre-fault state so we can get the most accurate backtrace possible. And that's sort of a block that does that here. My second poll, or my second thing I'm curious about, is if you've been doing debugging, have you gone about scripting the process and looking at it? And if so, what do you use? So we'll launch a poll here, and I'm curious to hear what you do. Save a lot of time scripting the analysis. All right, I'll give it a few more seconds. We'll take a look at the results here real quick. Not doing great today. I can't tell you how much time scripting the process or analysis has saved me over the years. So I really think taking a day or taking a couple hours to get that in place will save you a lot of time. All right, so we understand the foundations of what's happening and what's in place. What I want to talk about next is the class of faults that I particularly find the most challenging to debug, which is memory corruption. And what makes memory corruption so hard to debug or think about is that typically by the time you're executing an address that doesn't make sense or is invalid, something has happened in the past that has corrupted the system. And so when you look at that crash for the first time, it's figuring out what happened in the past that you'll have to do to actually fix the issue. And so what I have here, and we'll go through now, is a couple examples of that running on a very simple application using FreeRTOS on a Cortex-M MCU. And so when memory corruption takes place, the first thing I like to look at is there's 4 steps I usually like to look at. The first is whether or not that bus fault address register or Memfault address register are set. If that's set, we're going to know the exact access that failed on the system. Once we know that, there's a few things to check. We can check if that address is near a memory boundary. So something I always like to know and have written down when I'm working with MCUs is what the memory map for the platform looks like. This is the bytes the range that Flash runs on and the range that RAM runs on. And there might be multiple banks. If you see an access that's on the edge of those banks, it usually means your linker script is messed up, or you have started to roll past the end of a stack that was at the bottom of one of those boundaries. If you're not in that situation, the next thing to start looking at is where did that address that triggered the fault actually come from? And in that situation, there's usually one of 3 places. The address may have been a pointer that was in some static or global in your system. It could have come from a local variable on your stack, or something that was allocated in a heap if you're using that on your embedded system. And the reason it's important to find that initial location is a majority of the time when a memory or sort of a bus fault takes place, a corruption fault takes place, there's some neighboring buffer or allocation that has corrupted your state. And so once you've figured that out, what you can look at is what allocations are near that address. And this is where I like to go to sort of some of the tools in the ARM toolchain or the GNU bin utils. And it even has an argument where you can say, tell me everything in the symbol file and order it by the address it exists at. And so we can easily look for neighboring references. And so with that strategy in mind, let's take a look at an example. So on the left here, we have the world's simplest accelerometer driver. It just holds a pointer to a buffer called readings. And what we will do is batch up readings. And then there's a handler that will print the readings out and then run some processing on it. And on the right, what we have is a CLI command to exercise our driver. It takes an argument for the number of samples to generate. And then we set those samples to different values. And then we invoke this handler for actually running and looking at it. I'll give you a second. You might already see what the fault is here, but or what the fault could be here. But let's walk through a debug process. So what we're going to do here is load up the application inside GDB, and we're going to test that accelerometer routine with 9 samples. We're going to see that we hit a hard fault. So what's the first thing we do? We look at that configurable fault status register to see if there's any information there. And we can use that command we wrote to take a look at that. Cool. So it found that there's a bit set, and we know the exact address that triggered the fault, 0F0E008. So now we need to figure out, where did that bad address actually come from? So the first thing I like to do is look at the backtrace. So we're back in that situation where there isn't actually anything useful in the backtrace. So what we need to do here is restore our register state so that we can get something useful. All right, let's run the command. Cool, our backtrace actually looks good again. And so what we can do is start to walk through the frames. We see the pointer, that was the bad one. And then we see that it was coming from the SXL driver readings pointer. So now we know where we got the bad information from. But so what we want to look at is what is around the accelerometer driver in the address space. And for that, we can use that nm command we were talking about, sort it by address, and then search for references that are around it. And what we will see there is that the Excel sample buffer is directly above the Excel driver buffer. So that's suspicious. And when we print the sample buffer itself, what we see is there's a bunch of these 0F0E values. So what happened is we wrote past the buffer, and we corrupted the pointer, and that's what actually triggered the fault in the first place. So now let's take a look at what we could do to upper level or save us some time on doing that analysis ourselves. And what we do at Memfault is we actually have 2 main ways of analyzing the systems. We have a way of capturing it directly from your device, or we have a way of getting this information from devices that are completely out in the field. And so what you see here is a script that we can run on the device. It captures that memory snapshot, and it sends it up to Memfault for analysis. And what will automatically happen is there'll be a decode of that configurable fault status register we were talking about. And so we'll find out that we find out the exact address that happened. We find out that the error was precise. So that means we know the exact instruction which triggered it, which is a load instruction. That makes sense. We can look through the stack frames, and we can see right away, oh, there is an argument, the readings pointer, that was corrupt. We can walk up the stack and we can see, oh, there were 9 samples being generated that caused the issue. We can look at all of the globals and stacks that were collected. And by default, they're sorted by the address they appeared in. And so we can filter it down a little bit and see that there's an Excel sample buffer directly above the Excel driver buffer. When we expand that out, we see this bad pointer. We see that the buffer could only hold 8 samples. And so those 9 samples is what triggered our fault. let's take a look at another class of memory corruption. The stack overflow. So what we have here is a simple function. It's looking for a free flash page. It reads bytes from a page at a time. If they're not erased, it then calls itself recursively again. And so as you can probably imagine, if you call this too many times, we'll wind up overflowing the stack. Bad programming practice, you shouldn't do it, but I can't say how many times I've debugged faults or stack overflows that have been a result of some sort of recursive call chain. What's interesting with this one is it's actually going to be a fault that manifests from an exception handler itself. FreeRTOS will check for stack overflows when it is switching between tasks. And so when we look at our backtrace, what we get is an unwind to the hook in FreeRTOS that's checking for the stack overflow. And so what we could do at this point is start to look at the PSP and MSP and the state of the registers that was context switched out at the system, poke that into GDB and get the original backtrace as to what was happening. Or we can just shoot it up to Memfault for an analysis where it will run all of that for us. And what we get is that auto decode of the pieces there, but we get immediately that exception, that frame that was leading to the stack overflow in the first place. And so we see we made it through, I guess, 8 or so recursive calls here before it bailed. And so we know immediately we should probably just go and fix this recursive call chain. If it was some other type of overflow, maybe we would want to bump our stack. And then that initial exception we were talking about, the exception handler itself, is still captured, but it's less useful information in this setup anyways. Great. So we have a surefire way to look at and debug faults at our desk when we have a debugger. But what about all the faults? What about all the faults that we can't debug that way? Faults that happen out in the field. It's been said that 1/3 of all software faults take more than 5,000 execution years to manifest themselves. So if we go back to that original number, 4+ billion ARM microcontrollers in a quarter, we're looking at millions of crashes a year or millions of faults a year that are a result of this. But then there's another 2/3 of faults that are also happening more often and all the time. And so we need some strategy to be able to collect and look at this information so we can fix those issues that can lead to security flaws or returns on our devices in the field. And in order to do that, there's a few pieces of information that we will have to put in place. We're going to need to store the fault. We're going to need to persist the fault information on our device across a crash. We're going to need to push that info to the cloud for analysis. And once it's on the cloud side, we're going to have to write some infrastructure that's able to process and analyze the issue. So the first step that we can do ties back to what we initially learned. How do we figure out what stack was active when a fault took place? And to do that, we need to read that exception return value. That can be achieved by the bit 2 of that exception return value. And that will tell us if the main stack pointer or the process stack pointer was on the exception frame. And so we can take that and pass it into a function that does the handling. In that handler, we're going to need to save this information or state in some way. And there's a couple options we have there on our side to do that. We can persist the information in RAM, or we can save it to an external or internal flash storage. In this situation, we're going to look at how to save it in RAM. When information is saved across a reset in RAM, it's allocated in usually what is referred to as a no-init region. The no-init region needs to be an area that isn't touched by any part of your platform. So not the bootloader, not the main application, it can't be scrubbed. And so you're going to need to make sure it's marked off in your linker script. And so what we've defined here is a struct that matches that exception frame. And we've also defined a variable that's going to hold this information in that no-init region. When the HardFault handler takes place, what we can do is save the exception frame. And then we're going to use this magic header to mark that something was recorded. And then we're going to reset the system. When the system resets, what we're going to need to look at is we're going to need to look to see if there was a crash that took place. And if it took place, we can dump it to the console. Maybe you have a serial logger or something like that attached. We can clear that magic header so we don't keep thinking there's a fault, even if the system was rebooting as expected. And more importantly, we need to shuttle that data off of the device in some way. And so this is going to have to flow over your transport up to a cloud service to be decoded and analyzed. When it reaches the server, there's a couple strategies that can be used. One of the tools you can use is another bin util called adder to line. And what adder to line will do is it'll take an address and it'll take the symbol file. This is the file that's generated when you compile a build, and it will give you information about the function and line number where the system was executing. And so what we see here is we see the 2 lines from our initial buggy function example decoded, and we get the information of where they were at. The part that's important to note here is when you're sending this information up, you're also going to need some metadata so that you can locate the correct symbol file. As you're adding new features or tuning code space or changing your build, the locations of functions will move around. And so the server is going to need some way to look up the right one so you get an accurate decode and mapping. Once you've decoded and mapped the data, it needs to be stored in a database in some way. And from there, what you can start to do is look and see if there's trends. How many crashes, how popular are certain crashes, how many devices are impacted, what is happening there. So there's a lot of pieces in place that you need to have in place to get an answer to a very critical question for the stability of your platform. What you can do instead, if you don't want to go through that whole exercise yourself and you want to see the full stack traces and pieces, is use a tool like Memfault. And what we've done is we've implemented that fault handler to not only capture the registers, but also capture memory state or information. And then we'll even let you configure the regions that are collected so you can get different variables or system state as well. And then we'll automatically do that analysis and decode of the pieces that you saw. We'll look at that full stack trace and variable recovery. And the part that's my favorite is you can start to figure out what issues you should actually fix based on the impact they're having in the field. So here we have the 2 examples I went through from my desk, not many, just my device a couple times, so not a big impact. But you can have devices in the field that are seeing certain crashes thousands or tens of thousands of times across many devices, and you can know what to prioritize based on what's happening there. I hope you learned a little bit about HardFaults and how you would go about looking at them today. I'd love to hear your thoughts or other topics you think would be interesting to talk about. You can find me on LinkedIn. I listed my email here, or our interrupt plot. So I linked a little bit more information for some of the topics we went over today. The last one is the one I'd really pitch, the GDB Python scripting. It seems like that's not a strategy most people are making use of at the moment, and I think will save you a lot of time. Thank you.
Okay, so we'll be taking some questions from the audience for the remainder of the hour. So as a reminder, you may ask a question by clicking on the Q&A button in the bottom bar of the Zoom window. So we already have 5 questions, and I'll be asking Chris your questions, but don't hesitate to write up some more, and we'll get to as many as we can. So Chris, Bryce Wilkins asks, what tools do you recommend for scripting the register decoding? And have you ever used SVD files in that process?
Yes. Yeah, so in that article link, there is some information about the SVD files. The part that I've found challenging with SVD files is it's not, some vendors are decode more of them than others for you. And so you really want to kind of try a couple of different sets and make sure you have the right ones. There's even a Python package that will automatically load the SVD files and decode them for you inside GDB. So that's what I usually use there.
Thanks, Chris. Next up is Sean Hudson. who asks about a slide kind of earlier in your talk. He says the CSM bits you mentioned, I think this is a bit to set early on to make debugging easier.
Mm-hmm.
Can that be left active with no effects all the time?
It will only take effect so that register itself will only take effect when you're attached to a debugger. There's a bit the debugger will set to enable halting debug. And so if that bit hasn't been set by your debugger, it won't take any action.
Awesome. Thank you. Next, we have, and I apologize if I mispronounce the name, Niket Nedu, who said, rather than doing this via scripting, can the registers be written earlier? You know, the scripting of the recovering of the SP and other things, or even inside of the HardFault handler. I think you did touch on that a little bit. But perhaps there are there hybrid methods basically where your HardFault handler does some of the pre-work and then your debugger takes it from there?
Thinking about this one, there's definitely, so a lot of HardFault handlers will dump the register information out for you. And so when a HardFault takes place, one thing you could do is read that state and poke it back in. The part that would be challenging is if you updated the registers to their original value and tried to execute the code again, it would keep running or trigger another exception. So you'd want to have a breakpoint in place. But what I've seen work the best is sort of wiring up some automation for when the fault takes place to reset those registers or restore those registers back to their original value.
Awesome, and sorry about the keyboard noises there for a second. Aditya asks if there's anywhere we can find the code you just showed. So the GDB hooks and other things that you demonstrated, are there in GitHub somewhere in a repository they can look at?
Yeah, well, so I'll definitely publish the pieces that I put out today, but a lot of the examples can also be found in those interrupt posts that I linked at the end of the article.
And for those of you who aren't familiar with interrupts, you can find it at interrupt.memfault.com as Chris shared earlier. And alongside the interrupt blog is an interrupt GitHub repository where all the example code we use in our blog posts is shared on GitHub. So Aditya, that might be your best bet. David Bolchansky asks about Ozone. He said, have you ever used Ozone from Seger? How does that compare to your kind of current setup?
I have used it a little bit. I've heard really good things. About it. I've really gone far down on sort of the GDB scripting side. And so I'm not sure how to achieve those same results with the Ozone debugger, but it will give you all of this information and let you update registers and look at state as well. And I know there is some scripting facilities in there, though I haven't tried them.
We have one more question from Aditya who said, in your experience, are there faults that slip through and don't trigger any kind of handlers?
That's a good question. There's a couple things. So there's the situation where you fault from a fault. So imagine we fault from our HardFault handler. In that setup, the system would actually enter a mode referred to as lockup, and the processor would reset. And so something I like to always look at is when a system reboots, all the MCUs generally have a register you can read. Goes by like the name reset reason register or reset control register, reset cause. And that will tell you if this has ever happened. And so that's something that's really worthwhile to send up and look at as well. And something we track in our SDK at Memfault so you can trace down and look at those pieces. The part that's interesting from exceptions or other pieces is you can still catch those and look at it. So you can get to a state where very few faults trip through. And if they do trip through, if you're reading that reset reason register, you can find out if the processor was reset without the handler completing.
Tendai Makumire asks about imprecise faults. He says, with an imprecise bus faults, we don't know the exact instruction that caused the fault. Do you have any tips or tricks on our methodology we can use to recover that?
Yeah, so what I actually like to do there is ultimately the caching on Cortex-Ms isn't too deep, and so the fault, even if it's imprecise, the instruction which triggered it is going to be in that area or in that range. And so if you're looking at the assembly or inspecting the function, it's usually something around there that has tripped it up or made the issue happen. The features that can be useful here is some microcontrollers have options for tracing instruction execution or emitting instruction execution to RAM buffers on the device itself. And in that setup, if you have the instruction trace and you know it's a few instructions back, you can figure out what caused it as well. But it generally requires, for me, what I usually do is take a closer look at the code in the region by dumping the assembly with objdump and examining that way.
Nathan Jones asks about VC_hard error. And is that similar to halt if debugging functions I've seen before in some interrupt code example?
Exactly. So the cool part here is if you're flashing some binary that someone sent you, or you haven't added that type of infrastructure to your platform, it will effectively trigger the same thing. Instead of a breakpoint instruction in the code, what it will do is it will send a signal back to the debugger that the system has halted, and the same behavior will result.
Alexander Koltsov asks how large, excuse me, how large of a state needs to be stored for useful backtrace on a deployed device? Or is there a good rule of thumb of how much space should be set aside for core dumps for a good level of analysis? So maybe we can talk a little bit about what we recommend to our customers at Memfault.
Yeah. So what's typically there, what's useful to do if it's a bare metal device is something on the order of 400 or 500 bytes of the stack. We'll usually go through a couple frames and give you useful context about what was happening on the system. The bare minimum, you're going to want the register set that was active and a little bit of the stack so you can get the local variables in that frame and what was there. If you're using an RTOS or something like that, the state of a bunch of the registers is always going to be pushed onto the stack or stashed in a region when they're not running. And so that exception frame we talked about, plus a couple hundred bytes, will give us a few frames of the stack and something to operate on.
This is definitely the bare minimum. I'll add and say that this is an engineering trade-off, like many. So systems that have a lot of RAM and little storage have to make hard decisions about what kind of diagnostics they collect. But these days, oftentimes, if you have a SPI flash on your board, you've got 1 or 2 orders of magnitude more storage than you have RAM. And so in that case, you can often collect quite a bit more data. Matt Bonadonna asks about releases. So he says, when releasing a firmware build without any debug symbols, will it still be possible to debug faults given the methods used?
Yeah, so I guess there's one thing to note there. The final binary that's shipped to the device doesn't need any debug symbols or information on it at all. Like that can be stripped, and so it's not going to be on the device. But you are going to need debug symbols of some sort to map from. If you're collecting addresses on the system and you're sending those back, you need to be able to look up a symbol file to decode that. If you're saving other metadata like a git commit or something like that, or a version tag that the build is based off of, you could rebuild it after the fact and decode it there, but you are going to need some way to recover that ELF or that image that was built.
Devendra asks, I'll answer this one. Devendra asks if we provide any training related to fault management on Cortex-M. And so we do hold webinars semi-regularly, so keep an eye out for those. I'll also mention that we have a Slack channel that's connected to Interrupt. So if you go on the interrupts.memfault.com website, you'll find a link to sign up to the Slack. And there's a lot of troubleshooting that goes on in the Slack and developers helping each other. So I recommend you check that out. And last but not least, we do hold trainings for fault management and debugging with Memfault. So in the event you're interested in that, we're always excited to set up some time with you or your team and go through a training that covers both some regular general debugging techniques as well as how to use Memfault effectively to do this really well. And another question from Nathan, who says, is it safe to make subroutine calls from inside of a fault handler? For example, printf.
It's safe to make subroutine calls themselves, but a lot of implementations like printf under the hood will, depending on the platform, will wind up trying to grab locks or grab things that are interrupt driven themselves. And so generally you want to be very cognizant of what's actually running from the fault handler. And on a lot of systems, I would say printf would not work if it was called from a HardFault handler based on the implementation.
Next up, quite a few questions today. It's great that we had extra time.
These are great questions. I'm really enjoying them.
Next up is Jackson Burnett, who asks, I have found the DHCSR register and the debug gen bits that you mentioned earlier to be unreliable in the past. They can be sticky and they may cause a system to halt on exceptions even without a debugger attached. Have you ever seen this, and are there any workarounds?
Yeah, so the enable bit is sticky across unless there's a power on reset. So it's sticky across resets. So if you have a board where you are kind of connecting a debugger and detaching a debugger and sort of programming these values, it can get into a state where things are set, nothing is attached, and the system gets stuck. So the workaround I suggest there is if you're switching between those two modes, make sure to reset the board.
Next up is John Entz, who asks, what material would you recommend for learning or to use as a reference for GDB debugging? Most chip suppliers have Eclipse-based IDEs that use a GDB server, but the behavior is often different when trying to use GDB from the command line.
Yeah, so that is true. Most Eclipse projects also expose the GDB client in some way inside the IDE. But resource-wise, what I found most helpful has been the GDB docs. And then also I've written several different articles on our blog on the Interrupt blog about how to use GDB and how to look at some of the pieces there. But I would recommend trying it out or launching it and starting to poke around and look at it.
We have two more. So we have Mike Vojtovich, who asks, aren't there challenges to write a core dump to external SPI flash from inside of an exception handler? How do you typically approach this problem?
Yeah, so there's the main challenge is sometimes when these handlers are implemented, their driver will be interrupt driven and and so it'll rely on exceptions taking place or interrupts taking place to get the state. And so the way I usually approach the problem is you want to make sure you're using some pull-based driver to interface with the external SPI or quad SPI flash. And so if you're bringing it up yourself, it's something you can implement. If you're using a vendor SDK, there's often two modes that it can be configured in. Sometimes a bootloader will just use a pull-based implementation anyways. And so it's something you have to keep an eye out for and look at, but that's usually how to solve that.
The other thing is that whatever you're doing to write your fault information probably needs to bypass any kind of higher level software management. So for example, if you have a file system implemented on your flash chip, you likely will want to reserve a portion of your flash where no file system is implemented so that you can write from your fault handlers, because oftentimes when you're in a fault condition, your file system is unreliable. So I think to summarize, you want a portion of your flash dedicated to the error handling rather than a file in your file system. you want to write directly to it, and you want to use a driver that might be a minimal driver used only for faults, that doesn't use mutexes or doesn't use interrupts. So you're right, there are challenges, but we found that they're very much things you can overcome. Last but not least, oh, we have someone who sneaked in another last minute question. So David asks, do you ship your binaries with asserts, Seger prints, and other diagnostics message, or do you only have them in your dev environment?
I ship my binaries with asserts enabled. I think you want to be careful not to have asserts that are going to trigger boot loops or pieces like that. But the challenge or the problem I see often is when the asserts are disabled, a lot of them are catching memory corruption and other issues in the first place. And so by not leaving the assert in, for example, in like a FreeRTOS library, you'll probably eventually hit a hard fault because something got corrupted in the first place. And so on that side, I like to leave the asserts enabled on the system. For diagnostic messaging and error printing, can disable dumping it out to the console. But generally, I like the builds I'm using locally to be as close as possible to the builds that are in the field, so that we can catch issues on both sides.
Last but not least, Tendai Makumire asks, can we use these techniques on dual core ARM processors like the STM32H7 that have both an M4 and an M7?
Yes, yeah. So you're going to need, as long as your debugger is capable on the dual core processors, the debugger can attach to one core or the other. And so you're going to need to make sure you're on the right core when you're debugging. But the strategies and techniques we described are the same. Sometimes there's some bits or communication, some IPC between the cores where the M4 or the M7 can find out that the other one crashed. And so you'll want to like park the other core if a fault took place or a piece like that. But the same principles we discussed work.
Awesome. Chris, thanks a lot for answering. I think we answered 24 questions total. So some marathon question and answers. Thank you, everyone, for your thoughtful and excellent questions. Thank you for your time with us today and for your feedback. Colleen, I think you had a few things in closing, and we look forward to seeing you at the next webinar.
Thank you guys all again for joining. Just again, please take the survey if you have a few minutes. We'd love the feedback and get a chance to win an Amazon gift card. And we hope to see you at the next webinar also. Thank you.
Bye-bye.
Everyone.